This is your presenter, Asloob Mudassar, and I am presenting slide number 11 of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: spectra of alkali atoms, lifting of orbital degeneracy, screening of nuclear charge, spectral series in alkali atoms. Spectra of alkali atoms, lifting of orbital degeneracy. Out of the six, five alkali atoms are listed. For example, lithium 3, sodium 11, potassium 19, rubidium 37, cesium 55. And these numbers which I have written as a subscript, pre-subscript with these elements are actually the atomic number or the Z number of these elements. All these have a weakly bound outer electrons, the so-called valence electron. So there is one valence electron in each of these alkali atoms, which are further away from the nucleus in comparison with the inner core of the electrons. So each of these has inner core of electrons around the nucleus and one valence electron which is further away from the nucleus, which we call as the valence electron. Out of these, so each of them has the number of electrons, which we may say that these have a Z number of electrons. The rest of the Z minus 1 electrons are in the closed shells. State of an individual electron can be characterized by three quantum numbers: N, L, M. That is the principal quantum number, the orbital quantum number, the magnetic quantum number. There is another quantum number which is the spin quantum number. We are not mentioning the spin quantum number by now, but in the future we shall include, for example, in the next lecture we shall be including the principal quantum number also, the spin quantum number also. So there will be a four set of quantum numbers. But for the time being, we are assuming that we have a total of three quantum numbers which determine the state of individual electrons. So we are forgetting about at the moment about the spin quantum number. So state of an individual electron can be characterized by three quantum numbers: N, L, M. Principal quantum number, orbital quantum number, magnetic quantum number, and one quantum number which is the spin quantum number we are not mentioning by now. But we shall in the future lecture we shall include the spin quantum number also. The energies of electrons in a closed shell are strongly modified due to the interaction of electrons with each other when compared with an outermost valence electron. So in the inner core of the electrons, all these electrons may interact with each other, and so their energies are modified due to the presence of these electrons in a cloud of charge. But the valence electrons, since it is lying outside the inner cloud of charge, we shall say that the valence electron is not much affected by the presence of the inner core of electrons or the number of electrons present in the inner core. So now let's talk about the Pauli principle. At the maximum, two electrons can occupy a state with the given quantum numbers NLM, NLM. So if you are mentioning these three quantum numbers, then with these three quantum numbers, two electrons can be accommodated. So it means that there is something with other quantum numbers. So the spin quantum numbers will be included. So with that one, the two electrons can be accommodated with each of these states. So if we forget about the spin quantum number at the moment, we shall say that two electrons can occupy a state with a given set of principal quantum number N, orbital quantum number L, magnetic quantum number M. Ground state of an atom corresponds to the naturally occurring lowest energy state. So you see that when we say that the atom is in the ground state, it means that the atom is in its lowest energy state. So the ground state is usually regarded as the state with the lowest energy of the atom. Electronic energy configuration. Electrons in an atom occupy different energy levels, which are designated by unique terms. and which may be referred to as the electronic configuration. If there is a closed shell, as in the case of noble gases, the next electron added to the atom would occupy S state of the next principal quantum number n. So for example, in the noble gases, we have all the electrons in the closed shells. And if we add one more electron to the noble gases, we shall get the corresponding alkali metal atoms. And in the alkali metal atoms, the electron which we add to the noble gas will occupy the S state, and that will correspond to the next principal quantum number. These things will be clear in the today's lecture. It is not necessary that all the states belonging to the lower set of quantum numbers be filled. We usually assume that when we give a set of quantum numbers, when we specify a set of quantum numbers n, l, m, we assume that all the states below that quantum numbers are completely occupied or completely filled. This is usually the case, but not necessarily true. So closed shell electrons are closer to the nucleus than the valence electron and are most strongly bound. So in alkali metal atoms, we have the electrons in the closed shells and one electron, which is the valence electron, lying away from the closed shells of electrons. These closed shells of electrons are strongly bound to the nucleus. Closed shells are spherically symmetric and are especially stable. For example, in the noble gases, we have stable molecules of gases because they are chemically inert and highly stable. The total angular momentum of a closed shell is zero. So you see that all the electrons which are in the closed shell, their contribution towards the total angular momentum of the atom is zero. So the electrons in the closed shells will not be contributing anything towards the total angular momentum of the atom. So it means that the valence electrons will only be responsible for the contribution towards the total angular momentum of the atom, especially for the alkali metal atoms which has only one valence electron. So that one electron as the valence electron will contribute towards the total angular momentum of the atom. The alkali metal atoms are lithium 3, sodium 11, potassium 19, rubidium 37, cesium 55. These alkali metal atoms are followed by helium 2, neon 10, argon 18, krypton 36, xenon 54. So you see that the lithium has 3 electrons, helium has 2 electrons, sodium has 11 electrons, neon has 10 electrons, potassium has 19 electrons, argon has 18 electrons, rubidium has 36 electrons, rubidium has 37 electrons, krypton has 36, cesium has 55, and xenon has 54. The closed shells occur in the helium, in the neon, in the argon, in the krypton, and in the xenon. These elements are actually the noble gases elements, and they have closed shells. Now the noble gases have closed shells, chemically inactive with respect to the neighbors, have high ionization potentials, which decrease with Z number of the noble gases. That is, the electron in the helium 2 has a very high ionization potential. So if we move to the next elements, for example, neon has a relatively low ionization potential, argon has even low, krypton has even low, and xenon has the lowest ionization potential among these 5 noble gases elements. This is an example. For example, helium, if you add 24.46 electron volt of energy is given to the helium atom, it is singly ionized, giving you helium plus 1. But if you give 5.40 electron volt to the lithium atom is singly ionized. So here you can understand that for the alkali metal atoms, the ionization energy is relatively much lower in comparison with its counterpart in the noble gases. For example, the counterpart of the lithium in the noble gases is the helium. Singly ionized alkali atoms have closed shells with much high ionization potentials for the removal of second electron. So for example, if you want to doubly ionize the helium atom, that is you want to remove one more electron from within the closed shell of electrons, then it means that the ionization potential for such an electron will be much higher in comparison with the energy required in the first ionization potential. The electronic configuration of the alkali metal atoms is given. The electronic configuration of the lithium atom is 1s2 2s1. For the sodium atom, it is 1s2 2s2 2p6 3s1. For the potassium atom, it is 1s2 2s2 2p6 3s2 3p6 4s1. For the rubidium atom, it is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 5s1. And for the cesium atom, it is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 and 6s1. So you see that all these atoms have that is the alkali metal atom has have that the alkali metal atoms have one outermost electron which is labeled as 2s, 3s, 4s, 5s, 6s electrons respectively in the series of the alkali metal atoms. That is the outermost electron is the s electron. Simplified term or the Grotrian diagram of the alkali metal atoms compared to hydrogen atom is shown on the next page. The principal quantum number n is indicated and the orbital quantum number L is specified through the symbols. Capital S, when we are using a capital S term, it means that the orbital quantum number is 0. When we are talking about capital P, which is the term capital P term, for the capital P term, the orbital quantum number L is equal to 1. For the D term, the orbital quantum number is 2. For the F term, the orbital quantum number is 3. So we are in the next diagram, we are mentioning the principal quantum number, and along that the orbital quantum number will be included in the plot, but that will be included in terms of the terms, the spectroscopic terms, that is the S term, the P term, the D term, and the F terms. We shall be more about we shall be talking about in detail about these terms in the next lectures, but here for the time being bear with me that L is equal to 0 means that we are have the term symbol capital S. When L is equal to 1, we have the term symbol capital P. When L is equal to 2, we have the capital symbol capital D, and when L is equal to 3, we have the capital symbol capital F. So this is the a diagram that we are talking about. Let me read the caption of this diagram first. This is the term or the Grotrian diagram of the alkali metal atoms. And you see that we are plotting the energy on the left hand side in electron volt, and on the rightmost side we are specifying the principal quantum number 2, 3, 4, 5, 6 and so on for the hydrogen atom. So the hydrogen atom, the energy levels of the hydrogen atom is given on the rightmost side in terms of its principal quantum number 2, 3, 4. The principal quantum number n is equal to 1 has not been mentioned because it is lying much lower in energy. So if we include n is equal to 1, we cannot include the other energy terms with this resolution. So in order to improve the resolution of this chart, we have started the hydrogen atom with the principal quantum number 2. And you see that we have drawn a dotted line against the principal quantum number 2 level. Then we have also a dotted line. We have also a dotted horizontal line corresponding to the principal quantum number 3. We have a dotted line, a horizontal dotted line corresponding to the principal quantum number 4. Similarly, we have the dotted lines corresponding to the principal quantum number 5, 6 and so on. These horizontal dotted lines will provide you a reference with respect to the principal energy levels of the hydrogen atom determined by the principal quantum numbers, so that we can make a quick comparison. Now you see that and at the top we have the lithium atom, the sodium atom, the potassium atom, the rubidium atom, and the cesium atoms. And for these atoms we have four states for each of these valence electron, SPDF. And for the sodium we have SPDF, for the potassium we have SPDF, for the rubidium we have SPDF, for the cesium we have SPDF. It means that these SPDF correspondingly specify the orbital quantum number as 0, 1, 2, and 3. So it means that we shall be covering the orbital quantum number from 0 to 3. And you know that I have given different colors to this one. For example, the S element, the S symbol has been given a color which is light brown. The P symbol has been given the color green. The D has been given the color as red, and F is given the color blue, so that we can identify these lines very quickly. So now let's start for the lithium atom. The lithium atom, you know that for the we are specifying these. You know that I have written 2, 3, 2, 3, 4, 5, 3. You see that you can see the numbers with these lines, with these colored lines. These are actually the principal quantum number corresponding to different elements. For example, the lowest one is 2s, is the 2 and you know that it is just lying beneath the F symbol. So in the lithium you have the symbol F as the symbol S, and you know that below this symbol S I have mentioned its location, which is 2s. So 2 capital S is represented by this horizontal location. Then you see that we have 2s. Then we have, you know that when the principal quantum number is n is equal to 2, then what are the possible values of the orbital quantum number? The possible values of the orbital quantum number are 0 and 1. So with the principal quantum number 2, the orbital quantum number has two values, 0 and 1. So you see that I have plotted the value of 0, L is equal to 0 is plotted over here, and L is equal to 1 is plotted in green. So the principal quantum number is 2, and the green color represents that it is the P symbol. We are talking about the P symbol. For example, the P symbol is represented in green. For example, in the lithium, the P symbol is represented by green, and P symbol means we are talking about the value of the orbital quantum number as 2. So this term with the 2 green represents that the 2 is the principal quantum number, and green stands that here the orbital quantum number has a value equal to 1. So the first two term has been explained, that is the principal quantum number 2 for the lithium atom gives you two energy levels, one corresponding to symbol capital S, the other corresponding to symbol capital P. Now let's talk about the principal quantum number 3. When the principal quantum number is 3 for the lithium atom, then you know that when the principal quantum number 3, I have shown these three levels corresponding to state capital S, corresponding to state capital P, corresponding to state capital D. You know that when n is equal to 3, it means that there are three possible values of the orbital quantum number, starting from L is equal to 0, then L is equal to 1, then L is equal to 2. The L is equal to 0 corresponds to capital S symbol. The L is equal to 1 corresponds to P state. The L is equal to 2 corresponds to D state. So you see that these three states with the labeled with the principal quantum number 3, and their positions has been energy positions have been shown with the because of different orbital quantum numbers, and you see that these dotted lines with the giving you the reference line of the hydrogen atom for n is equal to, for the principal quantum number 3, you can see that these lines, one line is slightly, red line is slightly above this dotted line, whereas the two lines which is green and the light brown are lying below that one. So you see that you can compare that how the energy levels when the lithium atom is in the principal quantum number state 3 will occupy the states with respect to the hydrogen atom. Now, if you move to the principal quantum number 4 for the lithium atom, then you know that I have specified this 4 with each of these 4 energy levels. When n is equal to 4, then we have 4 values of the orbital quantum number starting from 0. So L is equal to 0 is represented under capital S, L is equal to 1 is represented under capital T, L is equal to 2 is represented in red under capital D, and L is equal to 3 is represented under capital F as blue line. So you can see that the energies of these lines with the principal quantum number 4 is below the principal quantum number reference level of the hydrogen atom for n is equal to 4. Similarly, we can show the other levels. Now you see that for the sodium atom, we have again the locations for S, P, D, F. So let's briefly discuss the sodium atom. For the sodium atom, we don't have we have the ground state which starts with the 3s, as you can see from the previous diagram. That for the lithium atom, the lowest ground state starts from 2s. Whereas for the sodium atom, the ground state starts with the 3s. And for the other, potassium 4s, rubidium 5s, and cesium 6s. So here you can see for the sodium we are representing the ground state. This is the principal quantum number 3, and with the orbital quantum number L is equal to 0. This state has been represented as the state corresponding to the ground state of the sodium atom. But you know that when n is equal to 3, then of course you have 3 values of the orbital quantum number. L is equal to 0 is represented over here. L is equal to 1 is represented over here in green, and L is equal to 2, L is equal to 1 is represented in red with the principal quantum number 3. So when the principal quantum number is 3, for the sodium atom, 3 states are possible. This is the ground state corresponding to the capital S state, and this is the first excited state shown in green corresponding to the P term symbol. And then we have the next higher state with the principal quantum number 3 is shown in red. So this corresponds to D state. So you see that with the principal quantum number 3, you can have 3 states for the lithium atom, and you can compare their energies with the energy reference of the n is equal to 2 level of the hydrogen atom and n is equal to 3 level of the hydrogen atom. Which are shown in the dotted line. You can compare the energies of these states these states with the principal quantum number 3 of the lithium of the sodium atom with respect to the hydrogen atom. So similarly, you see that when the principal quantum number is 4 for the sodium atom, we have 4 states, and you know that these 4 states have to be represented by 4 options of the orbital quantum number. So this state is principal quantum number 4, L is equal to 0. This green state is principal quantum number 4 with L is equal to 1. This 4 is the principal quantum number. This 4 over here is the principal quantum number. The principal quantum number is 4, but the orbital quantum number is 3. And then we have another 4. This is the 4th term. This is blue, shown in the blue, with the principal quantum number 4, and the value of L is equal to 3. So with the principal quantum number 4, we have 4 levels. First level with L is equal to 0. Second level with L is equal to 1. Third level with L is equal to 2. Fourth level with L is equal to 3, shown in the blue. So you see that these are the levels with which we have marked with the principal quantum number 4, and these 4 levels with L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3 are respectively shown in the light brown, in green, in red, and in the blue respectively. And you can also compare the energies of these levels with the reference to the hydrogen level energies, and also with the reference to the energies of the lithium levels. Similarly, for the potassium, the ground state is the 4s state, and you see that here is the ground state for the potassium atom. When you know that when n is equal to 4, we have four values of the orbital quantum number. So this is the ground state with the orbital quantum number L is equal to 0. This is the first excited state of the potassium atom with the L is equal to 1. And this is the third state of the potassium atom with n is equal to 4 and L is equal to 2. And this state is the fourth, is the state corresponding to principal quantum number 4. This is the fourth state with L is equal to 3. So you see that here in the potassium, when n is equal to 4, there are 4 states with L is equal to 0, with L is equal to 1, with L is equal to 2, and with L is equal to 3. So you see that similarly we have the ground states for the rubidium represented by 5s, and you know that when n is equal to 5, how many values of the orbital quantum numbers would be there? It would be 5 values. But in this diagram we are representing only the 4 values of the orbital quantum number. L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. So L is equal to 4 will not be represented over here. So with n is equal to 5, principal quantum number n is equal to 5, for the rubidium atom, we have 5 orbital states, 5 states corresponding to orbital quantum number. L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3, L is equal to 4. But since we have in this diagram, we shall only be specifying up to the 4 orbital quantum states. So let's see which states are these. So this is the state with principal quantum number 5 and L is equal to 0. This is the state with the principal quantum number 5, L is equal to 1. This is the state with the principal quantum number 5 and L is equal to 2. And this is the state with the principal quantum number 5 and L is equal to 3. So the state with the principal quantum number 5 and L is equal to 4 cannot be displayed in this diagram, because we have not shown the capital G term symbol over here. So we have shown only 4 symbols: capital S, capital P, capital D, capital F, which only specify the values of the orbital quantum numbers equal to L is equal to 0, 1, 2, and 3 respectively. So similarly, for the cesium atom, the ground state has the principal quantum number for the ground state is n is equal to 6 and L is equal to 0. Similarly, n is equal to 6, L is equal to 1, n is equal to 6, L is equal to 2, and similarly we have above states n is equal to 6 and L is equal to 3, and then the other 2 states cannot be specified on this diagram. So you see that what we wanted to show over here, we wanted to show that there are levels which also depend, besides the principal quantum number, on the orbital quantum number also. You know that in the hydrogen atom, you can see that there are levels. For example, n is equal to 2 level, only one level is present. For n is equal to, for the principal quantum number n is equal to 3, for the hydrogen atom there is only one level. For the principal quantum number 4 of the hydrogen atom there is only one level. For the principal quantum number 5 of the hydrogen atom there is only one level. But When we are talking about the lithium, sodium, potassium, rubidium, and cesium atoms, that the alkali metal atoms, you will see that besides the principal quantum number, n, there are splitting of the energies with respect to the orbital quantum number also. For example, if you look at the principal quantum number 4 for the lithium atom, you will see that there are 4 states, and these 4 states have been shown over here, and the energies of these have also been shown. So the first state with the principal quantum number 4 is L is equal to 0. The second one shown in green with L is equal to 1. The third shown in red is L is equal to 2. The fourth one shown in is with blue is L is equal to 3. So we have shown all these 4 states for the lithium atom. So it means that the energy of the atoms in the alkali metal atoms not only depend upon the principal quantum number n, but also depend upon the orbital quantum numbers. So here that's why we shall say that the orbital degeneracy is lifted. When we say that the orbital, you see that in the main topic I have included that the lifting of orbital degeneracy. Lifting of orbital degeneracy means that the energy of the levels now depends upon the orbital quantum number. So that's why we say that the lifting of orbital degeneracy means that the values of the energies are also now going to depend upon the orbital quantum number. So this is what I have shown over here. That is, the energies of these levels depends upon the principal quantum number n and also upon the orbital quantum number. So here for these alkali metal atoms, we can say that the orbital degeneracy is lifted. That is, the energies of these levels are also now dependent upon the value of the orbital quantum number. Whereas for the hydrogen atom, the orbital degeneracy is not lifted because the level 2 is not split into 2 states. The level 3 is not split into 3 states. The level 4 is not split into 4 states, and so on. So as far as the hydrogen atom is concerned, the orbital degeneracy is not lifted, whereas for the alkali metal atoms, the energies of these levels also depends upon the values of the orbital quantum number. So we can say that as far as the alkali metal atoms are concerned, their energies also depend upon the value of the orbital quantum number, and we shall say that the orbital degeneracy is lifted for the alkali metal atoms. So you should study this diagram in much greater detail along the vertical direction, and you should also compare the energy of these levels with the surrounding atoms. For example, if you are talking about n is equal to 5 and L is equal to 0 level of the potassium, you can also compare the corresponding 5 levels of the sodium and the rubidium, etc., to make the comparison that how the energy trend change. The comparison of hydrogen term diagram with the alkali metal atoms term diagram indicate that the L degeneracy for the alkali atoms is lifted. That is, the energy becomes dependent on both the principal quantum number and the orbital quantum number. As I have explained, alkali terms lie lower in energy in comparison with the hydrogen atom with the same principal quantum number. This is what you can confirm. For example, the n is equal to 2 level of the hydrogen atom occurs over here, whereas the n is equal to 2 level for the lithium atom occurs much below in energy than the hydrogen atom. So this is what I have stated in words. That is, the alkali terms lie lower in energy in comparison with the hydrogen atom with the same n. The smaller the L, the lower the terms in energy with the self comparison. That is, if you compare the energy terms, for example, the energy terms corresponding to a principal quantum number 4 of the lithium atom, you can see these 4 levels. And these 4 levels, you see that the L is equal to 0 level is lying in the lowest in energy. Then the next higher in energy is the L is equal to 1 state. The next to that one in higher in energy is L is equal to 2 state, and the next one higher in energy is L is equal to 3 state. So you can see that the energy of these states depend upon the value of the orbital quantum number L. So the lower the orbital quantum number, the lower will be the energy of these states. So the smaller the L, the lower the term in energies when with the self comparison. For larger N, the alkali terms are slightly different from hydrogen atoms. What is the meaning of this? You know that with the lower principal quantum number of the hydrogen atom, these levels lie lower in energy, the alkali metal atoms with the same principal quantum numbers. But you know that when the principal quantum number is very high, for example, n is equal to 5, 6, and so on, then you can see that the levels are also very close to that one. That is the energy gap between the corresponding between the levels or starting with the principal quantum number or in the alkali metal atoms, their difference would decrease with the energy difference would decrease as compared with the principal quantum number of the hydrogen atom. So initially the difference is larger. So if you start with the lower principal quantum number, for example, principal quantum number 2, the difference you can see is the difference with the principal with the same principal quantum number is much larger, corresponding to n is equal to 2. But when n increases, that is when principal quantum number increases, the difference becomes smaller and smaller. And with very large principal quantum number, you will notice that the states with the alkali metal atoms are very slightly differing from the energy from the corresponding hydrogen atoms when the principal quantum number is very large. So this is what I have stated, that for large n, the alkali terms are slightly different from the hydrogen atom. That is, the difference becomes smaller. Electrons with the smaller L are more strongly bound and lie lower in energy. So from the pattern, you have seen that the smaller L terms lie lower in energy. So it means that these terms are strongly bound to the nucleus. Now with increasing Z, the terms lie even lower in energy with same N, that is more strongly bound. With increasing Z, the terms lie even lower in energy with the same N, that is more strongly bound. For example, consider the level number 3, the principal quantum number 3 of the sodium atom over here. This the position, notice its position over here, and notice the position of the principal quantum number 3, the lowest level for the lithium atom. This is over here, and for the sodium atom, the same level is over here. So it means that as you increase the value of Z, which is in this diagram is towards the right, then what will happen? The difference of these would increase. So you can see that with the principal quantum number 4, the lowest level of the potassium atom is over here, whereas the lowest level of the lithium atom with the principal quantum number n is equal to 4 is over here. So you can notice this difference. So with the increasing Z, the terms lie lower in energy with the same N, that is more strongly bound. So here you can notice the energy difference between the, for example, between the level 3 over here and the level 3 over here. You can notice this energy gap over here, and then you can also notice a energy gap of the level 4, principal quantum number 4 over here, and also 4 over here. But you know that this is the position of the principal quantum number 3 for the sodium atom. and this is the position of the principal quantum number 4 for the sodium atom. So the difference has decreased with the increase of a principal quantum number. So notice the difference of the 4 over here and the 4 level of the lithium over here, and the third level of the sodium over here with the principal quantum number 3 and with the principal quantum number 3 of the lithium atom. So it means that with the increasing principal quantum number in the upward direction, the difference of energy terms with the same n value decrease as you go with the increasing value of z. That is, if you move to the right in the diagram, you will notice that this the difference would decrease. Now we are talking about the screening. You see that in the diagram I have presented over here, this is the diagram where the energy, where the orbital degeneracy is lifted. That is, the energy of these terms is now depending upon the value of the orbital quantum number L. Now, what is the source of this lifting of degeneracy? For example, in the hydrogen atom, we have seen that the orbital degeneracy is not lifted. For example, if the principal quantum number 2, there are two levels, but these two levels are overlapping each other, having the same energy. That is, these two levels are the degenerate levels. And similarly, for the hydrogen atom, when the principal quantum number is 3, there should be 3 levels. But all the 3 levels are the degenerate levels. And similarly, for the principal quantum number 4 of the hydrogen atom, there should be 4 levels, and these 4 levels are the degenerate levels. That is, they are the overlapped levels having the same energy. But this is not the case for the alkali metal atoms. There the energy depends upon the orbital quantum number also. Now the question is that the lifting of orbital degeneracy is shown in this diagram, but what is the source of lifting of this degeneracy? So let's talk about now the source of lifting of the degeneracy of the orbital degeneracy in the alkali metal atoms, and the screening concept in this connection is explained over here. You can see that I have shown the nucleus in the figure as the red dot in the center of this electronic cloud charge, which is the closed charge around the nucleus in the closed shells. So the center of the nucleus is indicated by the red spot, and there the total charge of the nucleus is Z times E, where E is the charge on the proton, E plus is the charge on the proton. So I have shown the radius R of this inner cloud charge, or that is of this closed shell. This is the closed shell. If it is the closed shell of the helium atom, it contains only 2 electrons. If it is the closed shell of the other atom, then it contains other number of electrons. For example, let me show. Over here, for example, the lithium atom, the closed shell, the lithium atom contains only 2 electrons according to the helium. And then the sodium atom has 11 electrons, but its closed shell contains 10 electrons. Similarly, the potassium atom has 9 electrons, but its closed shell will contain 18 electrons as shown by the argon. And similarly, for the rubidium, which has 37 electrons, and its closed shell will contain 36 electrons. The cesium has 55 electrons, and its closed closed shell will contain only 54 electrons. So you see that depending upon the element we are talking about, their closed elements will contain different number of electrons. So these are so this cloud of charge represents the number of electrons in the closed shell, and this will be represented by Z minus 1 times the charge of the electron. So these much charges are present in this closed shell, because the other charge is the outermost charge, which is the valence electron, is located at a distance r from the center of the nucleus, as indicated in this figure. And this charge, the valence electron, is represented by the green dot, and this is lying at a distance r much away from the inner cloud of charge. So for this electron, which is the valence electron, when you see the nucleus from this valence electron, you will notice that the nucleus charge will appear to be as plus E charge, because these electrons, which are the inner electrons around the nucleus in the closed shell, they will screen the nuclear charge by Z-1 times. And so this valence electron will see as if the nucleus has a charge as plus E. So this is called the screening. And due to this screening effect, because you know that in the alkali metal atoms, many electrons are present in the closed shells, and only one electron as the valence electron is present in the outermost shell of these electrons. So due to this screening effect and due to the presence of the number of electrons in the inner core, the screening effect will appear, and this effect will lead you to the splitting of orbital degeneracy. The model of screening can be used for the understanding of the term diagram of the alkali atom. So the term diagram that we have presented for the alkali metal atoms, that is this diagram, the splitting of the orbital degeneracy can be explained using the effect of screening. Valence electron is screened from the nuclear charge of plus Ze by the Z-1 inner electrons. So the inner Z-1 electrons around the nucleus will screen the nuclear charge by Z-1, and the valence electron will see as if the nucleus has only a positive charge equal to plus E. This requires that the valence electron should exist at a large distance r from the nucleus. So here you see that in the alkali metal atoms, we are assuming that the nuclear charge, that the valence electron, is located at a distance much away from the nucleus, from the inner core of the electrons also. And under that condition, we may write that the potential of the central potential of the central potential may be approximated to be equal to minus E square times over R if the nuclear charge is screened to 1 unit of charge. That is to the valence electron, if the nucleus appears as if it contains only one charge, then the potential will be written as if the potential is that of the central potential, and V of R is approximately given as minus E square over R. Now, if there is no screening, that is, you have the orbits which are also penetrating in the cloud of the in the inner cloud of the electrons of the cloud of the electrons. If the orbit of the valence electron is also penetrating inside that cloud of charge, that inner cloud of charge, then the potential is given by V of R is approximately equal to minus Z E square over R. And this is the condition under which if the valence electron is at a small distance from the nucleus facing unscreened nuclear charge Ze. So if the valence electron is very close to that one, then of course it will experience as if the nuclear charge is equal to minus Ze square over R. But you see that here I have shown a diving orbit. This is the orbit of the Sommerfeld model. That is, it may have an elliptical shape, and the orbit may dive into the inner cloud of the charges, and then it can move out of that in specific orbits, in specific elliptical orbits. So these are the diving orbits of the Sommerfeld. The nearer the valence electron approaches the nucleus, the more it experiences the unscreened nuclear potential. So you see that when the electron is much away from the nucleus, then of course the nuclear charge is screened by the inner core of charges. And when the electron approaches this nuclear charge, that is approaches closer to the nucleus, then of course the electron will feel as if the nuclear charge has the full charge. So the nuclear charge will be unscreened in that case, and it depends upon how much closer the valence electron approaches the nucleus. In the intermediate region, the electron in the diving orbit experiences a potential called V effect. That is the effective potential. That is when the electron is far away from the nuclear charge, the potential is given by minus E square over R. And when the valence electron is close to the nuclear charge but has not entered into the cloud or into the inner cloud of charge, then of course the potential seen by the valence electron will be equal to minus Z E square over R. And when the electron has entered into the inner cloud of charge, then of course it will have a potential which is called the V effective potential, which is no longer proportional to 1 over R. That is, the V effective potential is not a central potential. The concept of diving orbit does not exist in quantum mechanics. As in quantum mechanics, we talk about charge, we talk about the cloud of charge rather than the orbits, or we talk about in terms of the probabilities. Now you see that I have shown these potentials over here, the three potentials. So minus E square over R is the central potential, and this potential will be very applicable when the valence electrons is much away from the nucleus. And this is the potential minus Z E square over R is the potential seen by the valence electron when it is close to the nucleus. And then V effect of R is a potential seen by the electron when it dives into the inner core of the electrons. That is when the nuclear charge is not screened. Then the potential faced by the or experienced by the valence electron will be V effective. So let me read this statement. In the Summerfield picture, the diving orbits have different orbital shapes with different value of the orbital quantum number L and experience different degrees of screening. The probability density of the electrons in the neighborhood of the nucleus decreases in the order of L is equal to 0, 1, 2, 3, 4, and so on. So let me read again. Probability density of electrons in the neighborhood of the nucleus decreases in the order of L is equal to 0, 1, 2, 3, and so on. What is the meaning of this? The S electron are thus most strongly affected by the unscreened field of the nucleus. That is the X electron, that is the S electron corresponding to the value of L is equal to 0, can penetrate much stronger towards the nuclear region into the inner cloud of charge. So this is the meaning. And that with L is equal to 0, the electron with L is equal to 0 will penetrate more, and then will with L is equal to 1 will penetrate less, and even and so on. With higher values of the orbital quantum number L, the penetration will be smaller. Thus, for a given n, the energy terms of S electrons are shifted most strongly to negative values relative to the hydrogen atom. Because these are more strongly bound to the nucleus, will come closer to the nucleus during their elliptical orbits, then of course they will have energies which are they have more negative energies, that is their binding energies will be higher in comparison with that of the hydrogen atom. So you see that here I am going to explain the term diagram of the lithium atom. So you see that the energy has been plotted on the left hand side and the wave numbers have been plotted on the right hand side. And here the different transitions have been shown. Any value of n could be possible, but the transitions should obey this law, that is the change in orbital quantum number should be equal to plus minus 1. And you see that it should not be 0. So let me explain that one. This is the 2s level or the ground state level of the lithium atom. then you know that if the principal quantum number is 2, then there should be two states with the L is equal to 0 state is shown over here. Then L is equal to 1 state is shown as a 2p. 2p state is shown with the principal quantum number 2, and p means that the value of orbital quantum number is 1. Then you see that with the principal quantum number 3, I have shown 3 states. This 3s state means that principal quantum number is 3 and orbital quantum number is L is equal to 0. These 3p states mean principal quantum number is 3 and the orbital quantum number is 1. This 3d state mean this 3d state means that the principal quantum number is 3 and the orbital quantum number is 2. So I have shown these 3 states. Similarly, for the principal quantum number 4, there should be 4 states: 4s state, 4p state, 4d state, 4f state. And with the 4s state, we have orbital quantum number L is equal to 0. With the 4p state, we have orbital quantum number L is equal to 1. With the 4d state, we have orbital quantum number L is equal to 2. And with the 4f state, we have orbital quantum number L is equal to 3. And you can, I have also drawn the principal, energy levels corresponding to the principal quantum number for the hydrogen atom on the right hand side for comparison of energies. You can see that with the increase of orbital quantum number n, with the orbital quantum number L, the energies becomes same as that of the hydrogen atom. For example, the energy of the 4f state is close to that of the 4f of the hydrogen atom. 4, that the principal quantum number 4 of the hydrogen atom. So the 4f state of the lithium atom has an energy which corresponds to the n is equal to 4 level of the hydrogen atom. And similarly, I have shown for the 5 level for the principal quantum number of 5, since there should be 5 states for the principal quantum number 5. But you know that in this figure I can show only up to the 4 states. So this is the state 1, 4s, 5p, sorry 5s, then 5p, then 5t, then 5f, then there should be 5g also, which I have not shown because we are showing only the states up to L orbital quantum number equal to 4. So you see that for these one I have shown different states. Now I am going to show you the transition between these states. Any value of n is possible, and the orbital quantum number should change with plus minus 1. That is, when the delta L is equal to 0, the transitions are not possible. So delta L should change either by plus 1 or either by minus 1. So for example, consider the states from the 2s. So from the 2s, we have the transitions from the 2s to P2. Because S has L is equal to 0, this P has L is equal to 1. The difference between them is delta L is equal to plus 1. If you take the difference from P to S, then it is plus 1. If you take the difference from S to P, it will be minus 1. So the difference between 2S and 2P is being delta L is equal to plus minus 1. Then from 2S to 3P, you know that the principal quantum number is changing, but with respect to P and 2S, delta L is equal to plus minus 1. And similarly, the transition from 2S to 4P, the principal quantum number is changing. Any value of principal quantum number is allowed. And you know that the orbital quantum number is changed again by delta L is equal to plus minus 1. So from the level from the 2s level, the transition to all the p levels is possible. So the transition to 2p, 3p, 4p, 5p, and so on to the transition to all these p states will be possible. But you know that the transition from the 2s to 3s is not possible, because there the change in orbital quantum number will be equal to 0. So similarly, the transition from 2s to 3s to 4s to 5s and so on will not be possible. And similarly, the transition from 2s to 3d is not possible, because there the orbital quantum number will change by plus minus 2. And similarly, from the 2s to 4f levels, the transition is not possible, because there the delta L will change by plus minus 3. So the transition will only obey delta L is equal to plus minus 1. Now the transition from 2p can be taken towards the towards the S levels and also towards the D levels. But the transition from 2p to higher p levels will not be possible. So from 2p to 3s, from 2p to 4s, from 2p to 5s are possible. Similarly, from 2p to 3d, from 2p to 4d, from 2p to 5d are possible. And similarly, consider the level 3d. From 3d to 4f are possible. Similarly, from 3d to 4p is also possible. From 3d to 5p is also possible. That is, the transitions should obey delta L is equal to plus minus 1. And any value of n is possible. So this rule has been demonstrated for the lithium atom, but this rule that any value of n is possible, but only the orbital quantum number should change by plus minus 1 is applicable to all the elements of the alkali metal atoms. Now alkali atoms spectral series. There you see that in case of hydrogen atom we have observed some series, Lyman series, Balmer series and other series. They were discussed there. Similarly, we have some specific series associated with the alkali atoms, which we call as alkali atoms spectral series. The emission spectrum The emission spectra series from the neutral alkali atoms can be described by series formula similar to Balmer series formula. For sodium atom, the energy formula can be written as, you know that here the energy is now going to depend upon the two quantum numbers n and L. So E as a function of n and L is equal to minus, this is the Rna is the Rydberg constant for the sodium atom, multiplied with Hc, and then in the curly bracket we have 1 over square of n minus delta of Nl. You know that in the hydrogen atom we specified only the principal quantum number, but here we are specifying the principal quantum number n and also subtracting from it delta as a function of n and L, which depends upon both the principal quantum number and the orbital quantum number. That's why the energy written on the left hand side depends upon the principal quantum number n and the orbital quantum number L. And you see that this has been written on the right hand side as minus Rna, that is the Rydberg constant for the sodium atom, times H times C times 1 over n effect square. That is n minus delta n of Nl can be represented as n effective or n effective or the effective principal quantum number. So we have 1 over square of effective quantum number as shown in equation number 11.1, and here n effective is not an integer number. So now let me explain these terms. N effective is equal to n minus delta of Nl. This n effective, where n effective is a principal quantum number, generally not an integer. So for the sodium atom, we should take n effective as the principal quantum number, but we should keep in mind that this is not an integer, or generally not an integer. So if you solve this equation for the value of delta Nl, which can be written as the principal quantum number of the hydrogen atom minus the n effective, then you can regard this delta of Nl as the quantum defect associated with the quantum numbers n and L. So you see that this term is due to the screening fact. And since we are not going to discuss the idea quantum mechanically, so we are going to take granted from the quantum mechanics that delta of NL is regarded as the quantum defect associated with the quantum numbers N and L, and is related with the screening concept that I have discussed. So delta as a function of N and L is largest for S electron, because S electron is the electron which comes closer to the nucleus, and decreases for the p, d, f electrons. So for the other electrons which do not come much closer to the nucleus in comparison with the s electrons, so the quantum defect parameter, which is delta as a function of n and l, will decrease for the p electrons, even decrease for the d electrons, and also decrease further for the f electrons, and for the same atom is largely independent of n. So if we are discussing the same atom, for example, if we are discussing the lithium atom or the sodium atom or the potassium atom, that is for the same atom, the value of delta N of L is not depending upon the choice of the principal quantum number, but it will depend upon the orbital quantum numbers mainly. That is upon the s electron, upon the p electron, upon the d electron, upon the f electron, because the orbital quantum number is associated with these electrons. For the s electron, we have L is equal to 0. For the p, we have L is equal to 1. For the d, we have L is equal to 2. For f, we have L is equal to 3. So n as a function of NL, that is the quantum defect, increases from lithium to cesium. That is increase with in nuclear charge Z. So if you move from the lithium atom to the cesium atom, the value of this quantum defect delta will increase, because the inner cloud charge of the electrons now contains a greater number of electrons. The SPD, etc. electrons undergo different degrees of screening by the electrons of inner shells, and thus have different delta of NL. So for these values, the value of quantum defect delta, the value will change from S to P to D and so on. Their values are, the tables of these values are available on the net resources. Now this is the term or the Grotrin diagram of the sodium. Same rule is applicable. That is, the transition for any value of a principal quantum number is allowed, but only the transition should obey the value that delta L should change by plus minus 1. So here you can see that this is the S level. This is the 3s level. That is the ground level of the sodium atom. And the other 3 levels, because when principal quantum number is 3, there should be 3 levels, because the orbital degeneracy for the alkali metal atoms has been lifted. So when capital N is equal to 3, the values of L is equal to 0, L is equal to small l is equal to 1, small l is equal to 2 will be possible. So there should be 3 levels. So this is the first level, which is the 3s level. Then we have the 3p levels, then we have the 3d levels. And you know that the transitions from levels for any values of n is possible. Even you see that for the high values of the principal quantum number, the transitions are possible. And you know that we have shown over here the 2p3 half levels and the 2p half levels. So you see that if you look at this one, the 2s half and 2p3 half and 2p1 half, then the 2d3 half and 5 half and 2f5 half and 7 half. These are called the doublet terms. Doublet term means that each of these terms, due to the presence of the spin quantum number, will also split further into 2 terms. And you know that since we have not talked about the spin quantum number yet, up to the level of atomic physics that we have covered up till now, we have not talked about the or spin quantum number, and these terms are due to the spin quantum numbers. So 2s half will be only this is the only term that will be a single term. All the other two terms will be doublet terms. This is 3 half, 1 half doublet terms. This D contains doublet terms with total angular momentum of the atom as 3 half and 5 half. Then this F terms will also be a doublet term due to the total quantum number, due to the total angular momentum of the atom as 5 half and 7 half. And this 2 as a superscript represents the multiplicity. The concept of the multiplicity has been covered in one of the previous lectures. So the superscript before these symbols are actually the multiplicity. And multiplicity is given by 2s plus 1 represented by capital M. So in order to explain these doublet terms, let me go to the appendix and explain them very briefly there. For example, here you can see that this is the appendix, and here I am going to explain the doublet terms. This is the 2s half term. This is the 2p half and 3 half term. This is the 2d 3 half and 5 half terms. I am going to explain them. For this term, that is capital S, mean that L is equal to 0. And since only one electron, one valence electron is involved, so if there is one electron, we have the spin quantum number S is equal to half. Then you know that the total angular momentum of the atom is J, which is given by the mod of L plus minus half, L plus minus S. So put the value of L over there, which is 0, and put the value of half over there, and take the plus minus sign over there. You will get only one value, which is J is equal to half. And the multiplicity is given by 2s plus 1. Put the value of S is equal to half over here, then the multiplicity becomes equal to 2. So the term symbol is associated with the value of L. Since L is equal to 0, the term symbol is capital S. And the term is represented by M as the multiplicity, then the term symbol, and then the subscript will be J, which is the total angular momentum of the atom. So if you specify the multiplicity and J values for the symbol S, you will get this term 2s half. So let me now explain this 2p, 1 half and 3 half. For the p terms, we have the orbital angular momentum is equal to 1. Again, since only one electron is involved, as the valence electron, we have S is equal to half. The total angular momentum of the atom is J is equal to mod of L plus minus half, L plus minus S. And if you put the value of L is equal to 1 and S is equal to half and add them with plus minus sign, you will get 1 half and 3 half. Multiplicity is given by 2s plus 1, which is equal to 2, because the spin value is half. Term symbol is given by capital P, and the term is denoted by M, multiplicity M, then the term symbol P, and then J as the subscript. If you put the value of two values of J, then you will get this 2P. Multiplicity is 2, then P with the principal with the total quantum number of the atom there are two values, half and 3 half. Similarly, for the T atoms, we have L is equal to 2. The rest of the parameters are 3. J will be, you will have two values of J, 3 half and 5 half. Same multiplicity, the term symbol will be capital D, because for the L is equal to 2, we have the term symbol capital D, and the term is denoted by M and capital D and then J as a subscript. So if you put the value of two values of J over there, you will get 2D, 3 half and 5 half. So you see that here I have explained the doublet terms. So these are the doublet terms that I have explained. Okay. So you see that again the transition should obey all values of n, but it should particular obey delta L is equal to plus minus 1. And you can see that all the transitions are given with plus minus 1 over here. Now here I am going to talk about particularly the principal series represented in red over here, principal series. And the principal series lines have also been represented, shown in red. So all the red transitions are belong to the principal series. You can see principal series. The principal series starts from the S and it extends to all the P levels. Then the first secondary series represented in blue and shown from the P level to the higher to all the higher D levels. So this is the first secondary series from the P levels to all the higher D levels. Then the second secondary series shown in green from the P levels to all the higher S levels, shown in green. The transitions in green from the P levels to all the higher S levels form the second secondary series. Then we have the Bergman series shown in black, and the Bergman series, all the transitions from the level 3 of the D state to all the level F of the F state, to all the n levels of the F state. So here, since I have only 2 levels are present, I have shown only 2 black lines as the transition, but these transitions will extend to all the higher levels with principal quantum number of the F state. So these are the states, these are the 4 states that I have shown with their corresponding colors as indicated over here. And you know that I have also marked lambda 1, lambda 2, lambda 3, lambda 4, lambda 5 with these transitions. And these transitions in angstrom have been shown. The wavelengths have been shown over here. For example, for the lambda 1 case, you know that this is a sodium atom, and the lambda 1 case, I have shown the transition which is 5895.930. This is the D1 line of the sodium line, sodium transition from the 3p to 3s, or from the 3s to 3p. This is lambda 1, the sodium first line, and D lambda 2 is the sodium D2 line, which has a wavelength of 5889.963 angstrom. So the other lines are also shown. In the absorption spectra, normally the principal series is observed. Because the principal series is observed, it is because the principal series is the series which extends from the ground state of the hydrogen atom to the excited levels above that. And this can be observed at moderate temperature or at room temperature. But when the temperature is very high, for example, in the stellar space, the temperature is very, very high. So under that condition, the ground state, which is in the present case is the 3s state, will be shifted to some higher state. And then the principal series would not be observable, because the principal series is linked with the 3s state of the ground states of the sodium atom. So when the ground level is shifted because of the presence of the very high temperature in this stellar space, then of course this ground state will be shifted to the new state, and the principal state will not be observed, but other states can then be observed. So in the absorption spectra, normally the principal series is observed only because in the ground state of the sodium atom, the highest occupied term is the 3s term. The resonance line of the principal series is the transition from the 3s to 3p, or from the 3p to 3s, which is the sodium D line. The wavelength lambda 1, as shown in the previous spectra, is the sodium D line. Thus lambda 1 and lambda 2 are the sodium D lines. because they were the lines with the emission from 3s to 3p or from the 3p to 3s. And the double arrow shows that these are the resonant lines. What is the meaning of the resonant lines? Resonant lines that if you excite the atom from the 3s level to the 3p level, it will come back to the previous state, will giving off you the same wavelength or the same energy. Such levels are called resonant levels. So here the 3s and the 2 and these two 3p levels, these are the resonant levels. And the transitions for the resonant levels could be indicated by the double arrow over here. So these double arrow indicates that these are the resonance lines. The most important series in the principle is the principal series with the transition from p to s electrons. That is, the decay from these p state to the s state or the higher p state to the s state will give you the principal series. And the formula for the principal series is this: nu p in terms of the wave number is equal to Rydberg constant of the sodium atom, and within the square bracket we have 1 over n naught minus delta, and this delta has a value which is L is equal to 0, the square of this quantity, and then the second term which has 1 over square of n minus delta of n comma L is equal to 1. And here this principal quantum number n naught will start with n is equal to 3, and this n in the second term can take all the values greater than 3, which indicates that you are accommodating all the higher levels above the level n is equal to 3. This principal series is the principal series for the obtained from the sodium atom, because the 3s level will be the ground level of the sodium atom, and you know that here L is equal to 0. And let me show you that this is the 3s level with the principal quantum number 3, and this level will give you the orbital angular momentum, orbital quantum number L is equal to 0. Since all the transitions will end over here, that is from all the p states, the transition takes place to this state, which is the 3s state. So we have mentioned this one as the first term over here with L is equal to 0 and n naught is equal to 3, because this is the initial level in the sodium atom, and the transition since will takes place for all values of n, but you should take care that you should consider all values of n, but only those values which satisfy that the L should change only by 1. That is, you are talking about the principal series, and the transitions from all the higher p states to the state S is equal to 0, that is the state with L is equal to 0 will be considered. So this is the restriction that n naught will be equal to 3, for example, in case of sodium, and the principal quantum number n should be greater than n naught. Then the secondary series. So let me show you secondary series. The secondary series is shown in green. That is all the transitions from the S state back to the P state. That all the higher excited S states will decay to the P state. So the transitions from the S state to the P state will form the secondary series. And for the secondary series, we can similarly give the formula. This is represented by nu S, and this S stands for the sharp. So the subscript from the sharp S is taken as the subscript over here. So nu S means that the wave number is being specified with the S mean sharp. So again, we have the Rydberg constant of the sodium atom, and then we have in the square bracket two terms. In the first term we have delta, which starts with the n is equal to naught will be 3 in this case, and the principal quantum number, the orbital quantum number over here is L, because L stands for the p state. And since the transition has to be taken, will be decay from the L, from the or high from all the higher S states. So N, this N, since it indicates all the higher S states, it should be N naught plus 1, that is 3 plus 1. So if N naught is 3, then this N should start from 4 and higher terms. And this L is equal to 0 means that we are talking about the transition from S states. So transition from all the higher S states to the P states with principal quantum number 3 will form the secondary series or the sharp series, represented by the symbol S. So the next formula is for the diffuse series. For the diffuse series, we are choosing D as the subscript to represent this series as new D. So this is the diffuse series or the second series with the resonance from D to P states. So since the transition, let me show you the first secondary series first. Here is the first secondary series. The lines are shown in blue, and all the lines show that the transitions from the higher D states to the P states will take place and will give you the levels corresponding to the second secondary stage. So from the higher D levels to the P levels with N is equal to 3. So this is called the first secondary series, also referred to as the diffuse series, represented by the subscript D, due to diffuse. And a diffuse is another name for the second secondary series. And you know that again we have the Rydberg constant formula for the sodium atom, and then in the first term we have this delta contains N naught and 1. This one stands that all the transition will end up at the P levels. And here this P level exists for particular value of N naught is equal to 3. And since the transitions will take place from the D levels, so D, for the D levels we have L is equal to 2, and this N will take all values either 3 or higher values of principal quantum numbers. So this will be represented by the diffuse or the first secondary series. Then we have the Bergman or the fundamental series with the transitions from F to D transitions. So let me show you F to D transitions. Bergman series is shown in black. So the black transitions are shown over here. I have shown only 2 transitions, but many other transitions are possible from the higher F levels to all the levels of all the N is equal to 3 levels of the D state. So the principal quantum number for the lower state will be 3, and the orbital quantum number for the lowest series, for the lowest level of this series will be L is equal to 2, and the transitions from all the higher F levels will take place. So for all the higher F levels, the orbital quantum number is L is equal to 3. So you see that here I am representing this one as the Bergman series or the fundamental series, and I am choosing F as a subscript from the fundamental. So I have new F over here, and then again the new stands for the wave number, and then I have the the RNA, and then in the square bracket I have, you see that delta is now has 2 over here, because L is equal to 2 mean that all that the lowest level of this series will be the D series, and the higher levels and the upper levels of this series will be F series, that is F levels, which has L is equal to 3, and the which all these levels F levels will decay to the D levels, which is L is equal to 2, and the principal quantum number for that lowest state N naught is equal to 3. So all the higher levels will have N is equal to N naught plus 1, which is equal to 3 plus 1 is equal to 4. So n naught is the integral principal quantum number of the lowest state in the given series, whereas this n corresponds to higher is the principal quantum number corresponding to higher or the upper states of all the f levels for the example in this particular series. So you see that I have explained these formulas, and you know that the energies of these formulas not only depending upon the principal quantum number L, but also depending upon the orbital quantum number L also. That's why the orbital degeneracy is lifted in the alkali metal atoms. Here is the brief summary. The lowest state for the lithium atom for which the principal series occurs is the n is equal to 2 level. Similarly, n naught is equal to 3 level for the sodium atom is the lowest level for the secondary series. And n is equal to 4 for the similarly n is equal to 4 these are for other alkali metal atoms. So for the principal series for the alkali metal atoms, you have n is equal to 2 for the lithium, n is equal to 3 for the sodium, n naught is equal to 4 for the potassium, n naught is equal to 5 for the rubidium, n naught is equal to 6 for the cesium. And you know that, let me show you, n naught is equal to 3 for the n naught is equal to 3 for the sodium atom in the previous spectra, so that you can identify the things. For example, here this is the sodium, and you know that the lowest level here stands for n naught is equal to 3. Similarly, the other lowest level can for the other alkali metals have been specified as shown over here. The valency electron in each alkali metal begins with a new shell number. So for example, this is 2s, this will be 3s, this will be 4s, 5s, and 6s. Starts with a new principal quantum number. The principal quantum number of the lowest level in a series therefore increases by 1 to the next alkali atom with regard to its previous one, as obvious from this table. For example, the lowest level for the sodium atom starts with the 3. The lowest level of the potassium atom starts with the 4, and so on. The names corresponding to different values of L. The names corresponding to different values of the orbital quantum number accordance with the names given to different series are listed below. So this is the summary that I am giving you here. L is equal to 0, 1, 2, 3, 4, and so on. And the corresponding symbol is S, P, D, F, G, and so on. And S stand for the sharp, P stand for the principal, D stand for the diffuse, F stands for the fundamental. So you see that I have discussed the sharp series, principal series, diffuse series, and the fundamental series above, and their formulas with respect to sodium sodium atom has been discussed. Under the normal temperature conditions, only the principal series is observed by absorption spectroscopy. At extremely higher temperature, higher levels above the ground state are occupied, and the lowest occupied level at extremely high temperature is regarded as the new ground level. Because you know that when the temperature is very high, the normal ground level of these alkali metal atoms is shifted to higher level, and we regard such a higher level as the new ground level. Transition from the levels above this new ground level to this new ground level will produce other series. The lines of the principal series are thus the resonance lines. I have explained the word resonance to you. The best known is the D lines of the sodium atom, which is due to the transition from 3s to 3p or from 3p to 3s. This is the double-sided transition. That is, you can make the transition from 3s to 2p, and also the transition from 3p will decay to 3s, giving you the same wavelength. That's where these two levels are regarded as the resonance levels. If an atom has more than one electrons, then the capital letters can be used to designate an electron with its symbol. For example, capital S, capital P, capital D, capital F will be used instead of small alphabet S, P, D, F, etc. But if a single electron is involved, then small alphabets will be used as in alkali atoms. But you know that in alkali metals, in alkali atoms, you can either use small alphabets or you can also use capital alphabets, because alkali metal atoms are multi-electron atoms. So for the multi-electron atoms, considering the alkali metal atoms as the multi-electron atoms, you can use capital S, capital P, capital D, and capital F to denote different electrons. And if you consider that only a single valence electron are present, and if you include the screening effect of the internal electrons screening the nuclear charge, then you can consider this as if the alkali metal atoms are consisting of single electron, single valence electron, and in that case you can use small alphabets also. So both notations can be equally valid for the valence for the alkali metal atoms. So sodium atom series can be summarized as principal series from 3s to 3p. The lowest level is the 3s level. So the NP, the higher levels are the P levels, and N should the lower principal state, the lower state has the principal quantum number 3. The upper level will have all values of N greater than equal to 3. Similarly, second secondary series, the lowest level is the 3p level. The higher levels are the S levels, and the principal quantum number for these S levels can be any value with 3 or higher, with 4 or higher. The first secondary series, the lowest level is the 3p level, principal quantum number is 3, and the upper levels are the ND levels, and N principal quantum number can take any value greater than equal to 3. So I have given detailed description of these series, and here I have summarized them. Capital letters for term designation are for many electron systems, lowercase letters for single electron systems. In alkali metal atoms, there is only one valence electron, so the two term notations are equivalent. Screening effect of inner electrons can be calculated quantitatively if their charge distribution with sufficient accuracy is known. I am not giving you any formula for the calculation of the quantum defect of quantum defect numerically. I shall only have a qualitative discussion here. Let us calculate qualitatively the effect of the nuclear charge on a single 3d or 4s electron in the atoms of the hydrogen with Z is equal to 1 and the potassium with Z is equal to 19. You see that here I am going to make a comparison. You see that here we have we have already plotted the charge density of the 3d electron and the 4s electrons earlier in the chapter in the lecture on hydrogen atom. So let's see that can we get some information by analyzing such levels for the potassium atom, for the same levels of the potassium atom. Radial probability density or the charge cloud density for the 4s and the 3 and a 3d electron in the hydrogen atom is shown in the figure next. This is for the hydrogen atom. This is the probability density for the hydrogen atom for these two particular electrons. And this is normalized with the Bohr radius A0. So you can say that these are the distances which are equal to 10 Bohr radius, 20 Bohr radius, 30 Bohr radius, up to 50 Bohr radius. And on the vertical side, we have the probability density. This is the 3d electron shown in red and the 4s electron shown in blue. From the you can see that there is a peak corresponding to 3d electrons, and there is also a peak corresponding to the 4s electron. These peaks indicate the average time at which these electrons exist from the nucleus. So this 3d peak indicates that on the average there is a high probability that the 3d electrons occurs at a fixed distance from the nucleus, and the existence of the 4s electrons is further away from the 3d electrons as far as its probability is concerned. But you can see that there are small variations in the probability density of the 4s electron, and it appears that there is a finite probability not equal to 0 for the 4s electron close to the nucleus. It means that the 4s electron has a greater probability to come closer to the nucleus. The 4s electron on the average is further away from the nucleus, but the probability of finding it near the nucleus is greater than the probability of finding the 3d electron there. So if you look at this region, if you magnify this region, you will see that the probability of the existence of the 4s electron closer to the nucleus is greater than that of the probability of the existence of the 3d electron there. The 3d electron is more strongly bound to the hydrogen atom on the average, because it has a higher peak in comparison with the peak of the 4s electron. So on the basis of this one, we can say that the 3d electron is more strongly bound to the hydrogen atom. To conclude the analysis for the 4s and the 3d electrons, to conclude the analysis for the 4s and the 3d electrons in the potassium atom, let us first write down the electronic configuration of these electronic states. Now you see that actually we want to looking at the probability density plot for the hydrogen atom for the 3d and 4s case. We want to see that can we infer these informations for the 3d, for the 4s and 3d electrons in the potassium atom. Can this figure help us out in order to decide that which electron has the lowest energy in the potassium atom? That is either the 4s electron or the 3d electron. Which one of these two has the lowest energy in the potassium atom? So this is, you see that the electronic configuration of the potassium atom in terms of the argon atom. So you can see that it is the electronic configuration of the argon atom times the 4s electron, 4s1 electron, and the second one is the 3d electron. So these are the two possibilities that the last electron outside the closed shell of the organ will occupy either the 4s electron or the 3d electron in the potassium. This is what we want to determine, where the argon is the electronic configuration of the noble gas argon 18, and argon 18 has the electronic configuration as 1s2, 2s2, 2p6, 3s2 and 3p6. Following the conclusion from hydrogen atom, the answer about the more stable state for the potassium atom to be in argon and 3d1 state. So you see that if you apply the previous diagram, that is the knowledge from the previous diagram that is over here, we can say, for example, in the case of hydrogen atom, we notice that there is a more probability for the existence of the hydrogen atom in the 3d state rather than in the 4s state on the average, because on the average the probability for the hydrogen atom to be in the 3d s state is higher. And if we extend this one to the same case for the potassium atom, we would say that the electronic configuration of the potassium atom is the electronic configuration of the organ, and then we have 3d1. That is, the ground state of the potassium atom will be determined by the 3d1. 3D electron is the ground state electron of the potassium atom. But actually, this is not the case. Now, let's look at the following plot of the radial distribution for the potassium atom. The formula for the plot of the probability density for this hydrogen atom has been covered, has been discussed in the lecture on hydrogen atom. But as far as the radial probability density for the potassium atom is discussed, we have not given any formula for that one, but I have taken this useful plot for the probability density for the potassium atom. Here you can see that there is a larger peak for the 4s electron, but that is slightly away from the peak of the 3d electron. But the main point over here is that the 4s electron has a very high probability close to the nucleus. You can see that very high probability. If you look at close to in the region close to the nucleus, you will see that the probability of the 4s electron coming close to the nucleus is very higher. It means that the 4s electron is more strongly bound in comparison with the 3d electron. So on the basis of this one, we may have the following conclusion. The 4s electron in the potassium penetrates the inner core more effectively than the 3d electron. The Z effective, which is equal to 2.2 in this case for the 4s electron, whereas Z effective is equal to 1.0 for the 3d electron. The 3d electron is completely shielded by the inner core of 18 electrons. The 4s orbital is closer to the nucleus and is lower in energy than the 3d electron. Thus, the electronic configuration of the potassium can be written as the electronic configuration of potassium is equal to the electronic configuration of the organ, and then we have 4s1 there. So 4s1 electron will form the ground state of the potassium atom. And this will be the ground state configuration of the potassium atom. Calcium is next to potassium and its ground state configuration is 4s2. In hydrogen atom, energy mainly depends on n, that is on the principal quantum number, and on this basis the 3d electron orbital is lower in energy than the 4s orbital. So in the hydrogen atom, the energy depends only on the principal quantum number n. So that's why we can say that on this basis we can say that the 3d electron or the 3d orbital for the hydrogen atom has lower energy in comparison with the 4s orbital. In multi-electron atom like potassium, L is equal to 0 for the 4s, whereas L is equal to 2 for the 3d orbital. The higher value of S means more energetic and exists further away from the nucleus. So from the probability density of this plot, we can infer that the 4s electron has the more probability of penetrating in the region of the cloud charge, and it can come closer to the nucleus with more binding energy. So we can say that 4s state is the lowest state for the potassium atom. So 4s will form the ground state of the potassium atom. Next, the two spectra of the potassium atom are given. Next, the two spectra of the potassium atom are given. The first one presents the transition in visible and IR, whereas the second one, inner electrons are involved in the transition, and the transitions in IR, in the visible, in the UV, and in the X-ray are shown. X-ray spectrum includes terms with lower n than the visible spectrum. So n is equal to 1, 2, 3, and so on are labeled as K, L, M, and N shells respectively. So you see that in the next I am going to show you two spectra for the potassium atom. In the first spectra, the potassium atom will start from its ground state, which is the 4s state, and other higher states will be given. But in the second spectra, I am going to give you the spectra of the potassium atom starting from n is equal to 1. That is, I am talking about the inner electrons. And for the inner electrons, the transition in the inner electrons will give you the X-rays in the soft region, and those transitions will be labeled as K, capital K, capital M, and capital M and capital N respectively. So let's go through them. This is the term or the Grotrian diagram of the potassium atom. There you can see that the ground state is the 4s state. The other states have also been shown. And you know that at the top we are again showing the doublet states. Here the p doublet states are separated. The d doublet states have also been separated, but the f doublet state has not been separated because of the space. And you know that there is only one single term corresponding to S half. On the left hand side we have the energy display, and on the right hand side we have the wave numbers. And here I have the 4s electron, then 4p electron, then you see that 4d electrons, then of course 5s electron, 5p electron, 2 5p electrons because of the doublet terms. Similarly, we have 2 levels corresponding to 5d electrons, 2 levels corresponding to 4d electrons, 2 levels corresponding to 4p electrons. And similarly, if you go at the top, we have 2 levels corresponding to 6p electrons because we have the doublet there, doublet terms. And similarly, we have 2 levels corresponding to 5d electrons due to doublet terms. Similarly, 2 terms corresponding to 6d electrons. And I have shown only single terms corresponding to 5f and 6s, assuming that their separation with their doublets is negligibly small. As you can see that the 5d difference, that the difference of energy between these two 5d levels is very small. And of course, at the 6d difference, the separation between the two red lines of the 6d is also significantly small. On the basis of that one, I have only shown one for 5f level and one 6f level, indicating that these are actually single levels. And you see that these transitions have also, some transitions have been shown, and these transitions will follow the same rule as discussed earlier, that any value of n is allowed, and only the orbital values of orbital angular momentum will be allowed by delta L is equal to plus minus 1. So from the transition from the 4s to 4p transition are possible, but from the 4s to 5s is not possible. Similarly, from the 4p transitions to the 5s or to the 4d transitions are possible, but the transition from 4p to 5p are not possible. So you see that different levels in nanometers, different wavelengths in nanometers have been shown for the potassium atom. And you know that here the potassium atom starts from its ground state, which is the 4s state. Now in the next, I am going to show you another spectrum for the potassium atom in which the inner electrons are involved. Again, you see that I have shown the two terms, the doublets, the p doublets, the d doublets, and here I have also shown the f doublets. And I have shown the principal quantum number on the left side of this diagram. And I am now starting with the principal quantum number n is equal to 1. So it means that I am talking about the K shell. Here I have plotted the K shell. And according to the principal quantum number 2, there are L shells. And again, there will be n is equal to 2, means there are 3 L shells. L1, L2, L3. Corresponding to the principal quantum number n is equal to 3. Again, you see that there are the 3 levels, and these 3 levels are because we are also incorporating the spin quantum number over here, but we have not studied the spin quantum number yet. But you see that these doublet states, as I have discussed shortly earlier, that these doublet states are because of the involvement of the spin quantum number. So due to the presence of the spin quantum number, you will see that that against the principal quantum number 2, you have these three states, which is L1, L2, and L3 states. Their energies have also been shown, that is which level is higher in energy and which level is lower in energy. And similarly, for the corresponding to principal quantum number 3, I have shown three levels, M1, M2, and M3, and the other levels have also been shown. For example, to the principal quantum number 4, there are N1, N2, N3, and similarly N4 and N5. Two levels due to D doublets and two levels due to P doublets. In principle, these are basically three lines, but we have actually doublets over here due to the spin quantum number, which will be explained later. And this diagram will related with the emission of the soft X-rays will also be covered on the chapter on X-rays. So you see that here I have shown some particular wavelengths over here. For example, K alpha is equal to 3.74 angstrom can be obtained from the transitions shown over here. And similarly, I have shown K beta line for this transition. Similarly, alpha beta line is also shown for this particular transition. The other transitions are also possible, but I have shown only limited number of transitions over here. These transitions will also be discussed in a greater detail in the next lectures. That is why we have these doublets. What is the role of the spin quantum number over here, and how we can study these levels in much greater detail with more accuracy, and why we have these different nomenclature for the as far as the X-rays are related. We have K, we have L shells, we have then M levels, then we have N levels, and these will be explained when we shall discuss the detailed description of the X-rays. But here you can simply understand that these levels are present in this formation because we have the two P doublets. We have the two levels as the D doublets because the D has the doublets, which means two lines corresponding to capital D, two lines corresponding to capital P, and a single line corresponding to capital S. And similarly, two lines will correspond to capital F lines because these are the doublets lines having two values of the total angular momentum of the atom. And the energy wise of these levels have also been shown. Here you can compare that the energy of all the levels corresponding to n is equal to 2 are higher in energy than the K level, which corresponds to n is equal to 1. Similarly, the levels corresponding to n is equal to 3 are higher in energy than the levels corresponding to levels in 2. For the optical spectra in alkali atoms, valence electron could have only the principal quantum numbers. And these quantum numbers are listed as far as we are concerned with the optical spectra of the alkali metal atoms. That is the spectra in the visible region. For that one, we have some restrictions on the principal quantum numbers, which comes to us from the ground state of these atoms in the alkali metal atoms. For example, for the lithium, we have N should be greater than equal to 2. For the sodium, we have N greater than equal to 3. For the potassium, we have N greater than equal to 4, and so on for others, for other alkali metal atoms. All states with the lower n are completely occupied. That is, all the states in these corresponding atoms, the lower states with the lower principal quantum numbers in these corresponding atoms are almost completely occupied. I have not shown them in spectra. As the inner electrons are more strongly bound, such a transition takes place at higher energies. Because those transitions are not easy to activate because higher energies are involved. Energies in the range of soft X-rays are required if you want to excite the inner electrons of these levels. Such transitions will be discussed later in the forthcoming lectures. The transitions in the X-ray region of the spectrum are shown on the previous page, in which an electron is removed from a closed inner shell and replaced by a distant electron. So if you move an inner electron by providing some energy, or you ionize such an inner electron, then what will happen? An outer electron in the outer shells will come to fulfill the vacancy of the inner electron, and will of course emit some soft X-rays. This was all about the alkali metal atoms. And you know that in the alkali metal atoms, the main point I would like to emphasize is that the lifting of orbital degeneracy was discussed, and their reason was also discussed. This is an important factor, that how the energy of the different levels in the alkali metal atoms would also depend along with the principal quantum number, also on the orbital quantum number of the system. So this is the end of slide number 11 of the course on atomic and molecular physics.